Hi, this is the video presentation for Lesson 2 example problems. First of all, example 9.1. The problem is given a square steel bar shown and it has an applied axial tensile load of 95,000 pounds. Find the tensile stress. So the solution is, first you need to find the area, which is 2 square inches by 2 square inches, 4 square inches, and then we use our direct stress formula where the tensile stress equals the load divided by the area. We solve for the stress, which is 23 KSI. Now, 9.1b is similar, except that it isn't a square bar anymore. It's a W8 by 31 structural steel member, and it has the same load of 95,000 pounds. Find the tensile stress. Okay, so in Appendix A of your textbook has a lot of the properties of these I-beam sections. So all you need to do is to go to Appendix A and find the W8 by 31 table, find that beam in the table, and then you'll find that the area is 9.13 inch squared, and then we'll solve for the tensile stress, same as the last problem. Okay, example 9.3. What we have here is we have these 3/8 inch diameter rods, and they're supporting some pipes. It's in a process plant or something like that. So the allowable tensile stress in the rods is 24,000 psi. So find the allowable load in each rod. Okay, so first you need to find the rod area, which, pi over 4d squared to calculate the area of a circular section, and then calculate the allowable load. So you rearrange the direct stress equation. P equals the allowable stress times area, and I get 2650 pounds. Okay, so the next problem is a direct shear problem. Example 9.9. So given 2 steel plates are connected using 2 3/4 inch diameter bolts. A tensile load of 18,000 pounds is applied as shown. Find the average shear stress in the bolts. Okay, so in this particular case, what we're going to do is we're going to assume, first of all, that each bolt shares the load equally. Therefore, each bolt is going to resist 9,000 pounds. Okay, and then we need to calculate the shear area of the bolts. Okay, and the shear area, it's just as shown here with this jagged line here. So the shear area of the bolt is actually the diameter of the bolt. So then we're going to calculate the shear area, that's pi over 4d squared of the 3/4 inch bolts, and then we can calculate what the shear stress is in each bolt, and we get 20,400 pounds. Okay, example 9.10 is another example of direct shear. In this case, we have 3 wooden blocks that are glued together, and it's 2 of them sit on the table, and then a load of 50,000 kilonewtons is applied. So what we have to do is find the average stress in each joint. Okay, so first of all, we need to know what the shear area of one of the joints is, and that is this 75 millimeters high by 100 millimeters long. That's 750 millimeters squared. And then the next is we need to assume that of this load here, that each one of these shear planes carry half of the load. Okay, so therefore the load per shear plane is 25 kilonewtons. And then now that we have the load and the shear area per plane, we can calculate what the shear stress is. Okay, and that's P over A, which is 25 times 10 to the third newtons, divided by 7.5 times 10 to the third millimeters squared, and that gives us 3.33 newtons millimeters squared, or in other words 3.33 megapascals. Okay, so where do we get megapascals from newton millimeters squared? Okay, let me show you. Okay, so in stress, in system and international units, stress is in a Pascal. 1 Pascal equals 1 Newton meter squared. Okay, and so what I'm trying to do here is I'm trying to derive that 1 Newton millimeter squared equals 1 MPa, megapascal. So 1 megapascal equals 1 times 10 to the 6 Newton meter squared. So now let's convert Newton meters squared into Newton millimeters squared. Okay, and I'm going to do that by multiplying 1, which is 1 meter per 10 to the third millimeters, and square that. So when we do that, we have 1 megapascal equals 1 times 10 to the 6 Newton meters squared equals, multiplied by meters squared divided by 10 to the 6 millimeters squared. Okay, so essentially this is something that you need to recognize right off the bat, because in a lot of our problems in system international units, we're going to be working with millimeters, and by the time we're done working with millimeters, you're going to have a number like this. You're going to have units of Newton millimeters squared, and then what you need to do by analysis or just by recognition, look at that and say, that Newton millimeter squared, that's units of megapascals. Okay, so that's how we derived Newton millimeter squared equals megapascals. Okay, so here's another shear example. What we have here is a clevis arrangement with a rod that supports it. So given the clevis connection as shown, the rod has an allowable stress of 7,500 psi. Find the rod diameter to the nearest eighth of an inch. Okay, so this is a design problem. We're giving an allowable shear stress, and then we need to find the diameter of the rod. So solution. There are 2 shear planes, okay, one on each side of the rod, or each side of this bar in the middle. So there's 2 shear planes per rod, okay. So therefore the load per shear plane is 10,000 pounds. Next, we're finding the minimum area based on the allowable stress. So the area equals the load divided by the allowable shear stress, and that gives us a minimum area. Okay, when I say minimum area, if the area was increased, then we could carry more stress. If the area was increased, then the stress would be lower. So that's why I say this is the minimum area. Okay, so then what we do is calculate the minimum diameter based on the minimum area we calculated, and then increment that to the next eighth of an inch. Okay, so this d equals the square root of a over 4 pi. That's what this term here, 4, okay, 1.3. Okay, next example. It's about strain in a steel wire. I'm going to stop here just to keep this video short enough, and I'll pick it up in the next video.